Okay, welcome. Thanks, everyone. It's a pleasure to have Moses come over for the day. He has made the long trek from Whitefield to here, and the even longer is part of his trip to India from Stanford. So Moses is one of the leading computer science theorists in working in algorithms. He did his undergraduate degree at IIT Bombay and then his PhD at Stanford with Rajiv Motwani. He was a professor at Princeton for many years before moving to Stanford recently. Moses is going to, so I was particularly happy about the particular topic he chose for this because it's at an interesting intersection of mathematics, computer science, and physics even. So I hope, I'm looking forward to that, and he has promised to make it, since it's a proof from the book, it will hopefully be accessible to all of us. And being a Blackboard talk. Moses will also give a talk in the afternoon at 2 o'clock. So anyway, so over to you, Moses.
Okay. Well, thank you. Thank you all. Thanks for having me. I should say that I'm going to talk about something that I don't work in. So it's not an area that I work in, but there was a certain breakthrough in this area just in this year, this summer. And the amazing thing is that the proof of this is something that's very simple and can be appreciated by a lot of people. So I thought it'd be nice to present this proof. Okay. So what I'm going to do is I'm going to do this in an inverted order. Since I think I probably have most of your attention in the beginning of the talk, I'm going to give you the proof first, and then later I'll explain to you why it's such a big deal. Okay. So so I'm going to start with a simple combinatorial question. Okay. Let's say you have the n-dimensional hypercube. Okay, so this is 2 to the n vertices, where each vertex is labeled by a string of zeros and ones, right? And 2 vertices are adjacent if the bit strings differ in exactly 1 bit. Okay? Right? Okay. Is everyone, please stop me and ask questions if you have any questions. So everyone knows what the hypercube is? Okay? All right. I'll just introduce one piece of notation. If I have a graph on n vertices, then delta of G is just the maximum degree. Okay? All right, so just to make sure we're on the same page, what's delta of G for the hypercube? It's just n, right? So every vertex has degree n, so delta of the hypercube is n. Good. All right. There's a certain result. It's proved by a bunch of mathematicians. So it's proved by Fan Chung, Furedi, Graham, and Seymour in '88. Okay. And they said the following. If you take this hypercube, take a subgraph of the hypercube. Actually, take an induced subgraph. Okay, so what's an induced subgraph? You specify a set of vertices and then include all of the edges that go between 2 vertices in this set. Okay, so that's an induced subgraph. Pick an induced subgraph that has more than 2 to the n minus 1 vertices. Okay? Which means it has strictly more than half the number of vertices of the hypercube. And they showed that the maximum degree of this is at least half minus middle of 1 times log n. Okay, so notice that the degree of the entire graph is n. And they said that if you look at this induced subgraph, it's going to have degree at least log n. Okay? They showed that there is, okay, so they also constructed a particular subgraph on 2 to the n minus 1 plus 1 vertices with degree C log root n. Okay, so on the one hand, they showed a lower bound. They said that no matter how you pick your subgraph, it's going to have degree at least log n. There is one special subgraph that they constructed, which has degree at most root n. Okay, and people are interested in trying to close this gap. Okay, so right now we're just going to think of this as a mathematical question. Right? What's the right answer? Is it closer to this, or is it closer to this? Okay, so is the question clear? You take the hypercube, take an induced subgraph of the hypercube. This induced subgraph has more than half the vertices, and the question is, what can you say about the maximum degree of this graph?
Maximum over all the edges.
No, so it's what you want to know is min over all h, max over all vertices of the degree of V in H. Right? That's what you want to know. This quantity is delta H. Okay, and what you want to know is that for any subgraph H, can you guarantee, as long as the number of vertices in H is bigger than half, let's say 2 to the n minus 1, can you guarantee that there's at least one vertex that has high degree, right? So this is the quantity that we're interested in, yeah? So this construction says, well, there is at least one H such that this quantity is root n. Okay, so this quantity is no larger than root n. This says that no matter what H is, this quantity is always at least log n. Okay.
So with root n, you didn't say that that's the maximum you can have. Is that
okay, so this construction says that if you're interested in this quantity, right, of all the h's that you're trying to minimize over, there's at least one of them that gives you quantity root n. Okay, there could be others that are higher, right? But we're interested in the minimum one. We're saying.
So you want an optimal lower bound.
Yeah, we want to know what is the optimum lower bound exactly, right? And the answer is somewhere between log n and root n. Okay. So I just want to make sure. Is the question clear?
No, but it can't be bigger than square root of n.
Sorry?
It cannot be bigger than square root of n. There's a upper bound also.
Well, clearly you can just take the entire graph, right? And that's going to have degree n. So there are definitely going to be h's here, subgraphs h, that have very high degree. I want to know, can there be induced subgraphs of very low degree? That's the question.
Okay, it's on the lower side.
Yeah. I want to know, if I look at so the thing is, I'm looking at the maximum degree of a subgraph. Okay, so when I look at a subgraph, I don't care about the fact that some of the vertices are low degree. As long as there's one vertex of high degree, I'm fine. Okay, so for a subgraph, the object of interest is the maximum degree, right? And now I'm saying, can you find, do there exist subgraphs such that no vertex has high degree? Right? That's the question. And the answer somewhere is between log n and root n. Okay? Right, so again, is the question clear? You had a question?
I thought you said, so you found something that has root n. So the answer, the optimal lower bound would be at least.
So this quantity, okay, this quantity is sandwiched between root n, okay, because in this minimum, at least one of these subgraphs you should consider as this one, and that's going to give you root n, right? And this says for every h, no matter what h you consider, every h in here, this is at least, log n, right? So what we want to know is, can we narrow this gap? Okay? Okay, good. And the theorem I want to tell you about is that in fact delta H is at least root n. Okay, so for every subgraph H, there exists a vertex of degree at least root n. So in fact, root n is the right answer. All right? So this is the theorem we'll prove. And at this point, it's just a theorem. And then later we'll see why this is actually an important question. Okay? So the statement of the theorem is very simple, right? We just stated it. I should say one thing. Let's just check let's check our understanding. In this statement, we said we're going to look at induced subgraphs that have at least strictly more than half the number of vertices. Okay, so let's ask ourselves why we put that restriction. Anyone? What happens if you remove that restriction? Yeah, so one thing is if you look at the hypercube, right? You can just look at, 1/2, slice it along one dimension, and look at the, well, actually, no, that's not a good one. Let's do another different construction, sorry. Let's look at the odd parity vertices versus even parity. Okay? So if you look at the set of vertices that have even parity, that's exactly half the number of vertices, and there's no edges within this set, right? Because every edge goes between an odd parity to even parity. Yeah? So it's really important that I said that you have strictly bigger than half the number of vertices, because if I allow for half the number of vertices, there's something which has delta H equal to 0 in this case, right? Okay. All right, good. Okay, so I'm going to prove this theorem now.
So you have just all the odd. So odd parity is just where the number of bits, there are odd number of ones or odd number of.
Yeah.
Right?
Yeah. So H, right? So let's define it. H is the set of vertices. I don't know. It's a sequence of n bits such that let's say the sequence has odd number of ones. Yeah. You were going to say.
So supposing you take that and then you add one more from the even one. So that will have n, I guess.
That'll have n. Yep.
But the one that was constructed is a little more subtle.
Yeah. Actually, it's not clear how to even construct. So if you're getting bored, you can try to see, can you construct a graph which has so many vertices to the n minus 1 plus 1, where the maximum degree is at most root n. It's not easy, it's not trivial, okay? Somewhere later, maybe we'll see a construction, but it's not clear how to do this, as Rajesh pointed out. If you just take this one graph, which happened to have exactly half the number of vertices with degree 0, adding any one vertex to this is going to give you degree n, right? So you need to be a little cleverer. This thing doesn't work, okay? All right, so we're going to prove the statement, right? So in order to prove the statement, we're going to take a little bit of a detour. We're going to forget about the statement for a while, and we're going to construct some matrices. Okay, so, and then hopefully very soon we'll see why this construction is somehow related to this fact that we want to prove. Okay, so I want to prove that theorem now. Okay, so we're going to construct a sequence of 2 to the n by 2 to the n matrices. Okay, and call this an, and the construction is going to be as follows. It's going to be a recursive construction. Okay, A0 is just a 1 by 1 matrix, and it will just be 0. Okay, and an will be recursively defined. We'll define it to be an minus 1, a minus an minus 1, identity on 2 to the n minus 1 vertices, the identity on 2 to the n minus 1 vertices. Okay? So this is the construction. Okay, so right now this is just some construction of a matrix. This is a 2 to the 0 by 2 to the 0 matrix. By induction, this is going to be a 2 to the n by 2 to the n matrix. Okay? Okay, good. So that's the construction. Let me prove some properties about this construction. So the claim is that if you look at an squared, this is n times the identity. Okay, let's prove.
Similar to the way in which
Sorry?
it looks similar to the way in which different algebras are generated to the end.
Yes. Yes. In fact, there is a connection. I don't know about this connection, but I know it exists. And maybe in the very end, I'll say a little bit about some other interesting things around this. And in fact, one connection is the one that you just pointed out. Okay, there's actually is a connection to Clifford algebras. Okay, but our presentation is going to be completely elementary. We're not going to use anything about all of these things. Okay. All right. So let's prove this. Okay, it's very simple. Let's just verify. So an squared is the square of that construction. So an minus 1. Identity on 2 to the n minus 1. Okay, so let's just verify. So what happens when you multiply this with that? You get an minus 1 squared plus identity 2 to the n minus 1. The other diagonal entry is going to be the same thing. An minus 1 squared plus identity on 2 to the n minus 1. This one should be 0. This one should also be 0. You can verify it's the case. Okay. And then by induction, you're done. Okay. All right, so we proved this. Good. Okay. This says something about the eigenvalues of this matrix, right? We're going to plus or minus root n. okay? And we'll come back to this, talking about the eigenvalues in a second. I want to say a little bit about what this matrix is. So, sorry?
Half of them plus root n and half of them minus root n.
Half of them plus root n, half of them minus root n. Good. So from this fact, we know that the eigenvalues of an are either plus root n, minus root n, half of them are plus root n, half of them are minus root n. Okay? All right. How is this related to the hypercube? So I want to somehow connect this to the hypercube. Right? We started out with the hypercube. Okay, so in order to do this, let me look at two vertices and let's look at their bit sequence. So alpha is a1 up to an, right? Beta is b1 up to bn, okay? And my claim is that if you look at the alpha beta entry of this matrix an, this entry is non-zero. So first of all, what are the entries of this matrix? So the entries of this matrix are either 0, +1 or -1. Yeah? These are the only values that you can get. Okay? So the entry is non-zero if and only if alpha, beta are adjacent in the hypercube. Okay? We'll just check this fact. It's not very hard to check. Okay, so let's check this.
Alpha beta is a way of labeling the entries. So, the string you label in the same way as you label the hypercube. So
Yeah.
it's binary labeling.
Yeah. So this is subject to some appropriate labeling of. So right now the rows and columns just go from 0 to 2 to the n minus 1. I need to label them in some way so that I have this property. So I'm going to give you this. I'm going to tell you how to label this. Okay. So I'll do this proof by picture. So an, okay, is, remember, an minus 1 minus an minus 1, identity on 2 to the n minus 1, identity on 2 to the n minus 1. Okay, right? Let's label these rows, the first half of the rows, by bit strings that start with 0 and then go from a2 up to an. Okay? Let's label the second half with bit strings that start from 1 and then go on to a2 up to an. The columns, let's use 0, b2 up to bn, and 1, b2 up to bn. Okay? That's the labeling. And now notice that what does it take for this to be adjacent to this in the hypercube? So they already differ in the first bit, which means that the remaining bits have to be identical. Okay? And in fact, we do have a diagonal matrix here. Okay? Same thing out here, right? This and this already differ in one bit, and indeed you have a diagonal matrix here, which is great. What about this and this? Well, in this case, they agree on the first bit, which means that they have to have exactly one bit different in the remaining n minus 1 bits. So you really have a hypercube on n minus 1 bits. And indeed you have this matrix an minus 1, which recursively you've proved has this property. Okay, and the same thing here. Okay, so in fact this an, what is this an? An actually is just if you look at the adjacency matrix of the hypercube, this is a particular signing of the adjacency matrix of the hypercube, right? It just says, let's look at the hypercube, let's look at the adjacency matrix. Adjacency matrix just has zeros and ones, but now we're going to introduce signs in this adjacency matrix in some way, and that particular way is this one. Right, so that's all we did. Okay, so far so good? that was determined by this construction, right? So if you really want to know, then we can sort of figure out. So, okay, where are you going to get the minus ones? You're going to get the minus ones only when you fall here, okay? So for a while, let's say, so you have two vertices that differ in exactly 1 bit, and you want to know, in the final construction, what is the sign of that entry going to be, right? So you can determine it from this, you sort of figure it out in this way. So, okay.
Is there a geometric way to characterize that plus or minus?
Yeah, so I'll give you a way to characterize it just now. We can do this here. Okay. So let's look at this 2-bit sequences that differ in exactly 1 bit. Okay. So for a while, they agree. Okay. So initially, there's a sequence where they agree. So zeros, they agree. Then you have ones, you have zeros, and you have ones, so on and so forth. Okay? And then finally, you have a bit where they are different. Okay? So when they agree on the first bit and they both happen to be zeros, you go into this part. Right? When they differ when they agree and the bit happens to be 1, you go into this part. Okay? So every time in the prefix of the sequence where they agree, whenever you encounter a 1, you have a negative sign, right? So you're going to have -1 raised to the number of ones in the prefix where the strings agree. Okay?
That's where this Jordan-Wigner transform.
Yes, exactly. Okay? So eventually what's going to happen is that then you have this bit where they are different. At that point you go into this part and there's no more sign changes. Okay, so now we have an explicit characterization of what exactly this matrix is. It's -1 raised to the number of ones in the prefix where the two sequences agree. Okay? And as Rajesh correctly pointed out, this is very closely related to something called the Jordan-Wigner transform, which I don't know much about at all in physics. Okay?
So -1 occur when you're predicting different parity edges, is that?
So first of all, we've already realized that for you to have a non-zero value, +1 or -1, it has to be the edge of a hypercube. So these two sequences have to differ in exactly 1 bit. If that's not the case, then the entry is 0. We know that already, right? So now we're looking at 2-bit sequences which differ in exactly 1 bit, and all we're asking is, what exactly is the sign of this entry? It's either +1 or -1. What is the sign? Okay. So now we actually gave an explicit characterization of what the sign is. Look at the two sequences, right? They consist of the following form. It's S1, 0, S2, S1, 1, S2, right? They have to be of this form. And then the sign is exactly -1 raised to the number of ones in S1. That's basically what it is, right? That's from this construction, but now given an explicit form.
It's the parity of that bit, of that vertex.
But if you take the difference, what's going to happen is S1, you'll get all zeros here. You'll get 1 over here and you'll get all zeros here. Then you lost information about what the ones were in S1. Right? So it's something a little bit different. Okay? Yeah.
Can I ask you something? Can you write down a few examples of this matrix?
This matrix?
Yes, 4x4, let's say.
Okay, let's try it. I haven't done it myself, but we can try it.
They are related to just some sorts of Pauli matrices. That's what you're saying. Clifford has, but they are essentially gamma matrices.
Yeah.
I see. So I worked out
Yeah, it's interesting. So what's interesting is that when I read this, people mention these connections, right? It's easiest for me to think about it like this, but it's easiest for you to think about, you know.
Because we work in n-dimensional
Yeah.
And the mind is immediately
because that's the spinorial representation of SO rotation.
Yeah. Okay, so let me just write down a few, like the initial few matrices. Just
it is that.
I believe you're correct. Yeah. But maybe should I write it down or should I not? No. Okay. All right. Fine.
Three or so. We can get that. Just the first three.
Yeah, like 0, 1, 1.
Okay. Sure. So okay. A1 is just 0. Okay. A0. Okay. What's A1? So A1, let me do A1 over here. So A1 is going to be 0, 0, 1, 1. Okay. A1, A2 is going to be, well, I have to have 0, 1, 1, 0. Then I'm going to have 0, minus 1, minus 1, 0. And then here I need to put identity. Here I need to put identity. Okay. And now, well, I don't know if I have space to do this, but okay, good. I have to say, we're not going to use any of this stuff. Like, I don't really, in this proof, I don't care about what this explicit form of this matrix is, although it's useful to know if you want to connect it to other things that you're familiar with, okay? So, I actually never wrote this down myself. Yeah?
So this this 2-1 block would be diagonal.
Oh yeah, that's right.
Yeah.
Okay. Yeah. So yeah, we're not going to use this fact at all. Okay. Okay. So, so we already made this observation that from this fact, the eigenvalues of an are either plus root n or minus root n. There's actually half of them at plus root n, half of them at minus root n. I'm going to give you an explicit characterization of what the eigenvectors are. Okay. Because this matrix is very nice, we can actually write down explicitly what the eigenvectors of this matrix are. Okay, I'm going to try to leave this thing here because this is what we're trying to prove. Okay, so I define an over there. I'm going to define bn, which is 2 to the n times 2 to the n minus 1 matrix. Okay? And bn is going to be defined to be an minus 1 plus root n times the identity. And here I just have the identity. Okay? All right. So bn has rank 2 to the n minus 1, right? Because you have this whole diagonal block. All right? And let's look at an times bn. Okay? So an was an minus 1, identity minus an minus 1. Okay? And bn I just defined up here. An minus 1 plus root n times the identity. Okay. And if I multiply this out, what will I get? So I need to multiply this with this. So you will get an minus 1 squared. Sorry, what should I get? Yes. plus root n times an minus 1. And what else do I get? Plus the identity. Good. And what do I get down here? I should get an minus 1 plus root n identity.
An minus 1 cancels.
Oh, that's right. Okay, good. So that's going to cancel. I should really get root n times the identity. Okay? Now remember what we said over here. An minus 1 squared is n minus 1 times identity. So this whole thing is going to be root n times an minus 1 plus n times the identity. And here I have root n times the identity. Okay? So an times bn, I'm going to leave this panel. I should have written it somewhere else, but I'm just going to leave it as a reminder of what we're proving. Okay, so we proved that an times okay. So these are just the eigenvectors corresponding to the eigenvalue root n. You just happen to have a nice explicit representation for them. Okay? Okay, so now I'm going to go back to this statement. Remember, well, we really have a hypercube. We have an induced subgraph of the hypercube, H. And we want to make some statement about the maximum degree of this induced subgraph. That's what we really want to do, right? Okay, so let's look at the vertices that do not belong to H. How many such vertices are there? Well, H has 2 to the n minus 1 plus 1 vertices at least, right? So by the way, we're interested in the induced subgraph. If it happens to have more than 2 to the n minus 1 plus 1 vertices, we can just get rid of a few of them. Doesn't matter. The maximum degree will only go down. So let's say H has exactly 2 to the n minus 1 plus 1 vertices. Okay? Now, let's look at the vertices that do not belong to H. And let's look at, in the matrix B, let's look at the 2 to the n minus 1 rows corresponding to these vertices. Okay? So for indices, yeah, not in H. So Bn, remember, had 2 to the n rows, right? One corresponding to every vertex of the hypercube. Okay? I'm interested in a subgraph on 2 to the n minus 1 plus 1 vertices. Look at the vertices that do not belong to H, and let's focus on those rows. That's B star. Okay? So B star is a submatrix corresponding to these rows. Yeah? Okay, so we can find a non-zero 2 to the n minus 1 times 1 vector x such that B star of x equals 0.
Find the non-zero one, 2 to the n minus
2 to the n minus 1 times 1. Just a column vector. Okay? It says that B star of x is equal to 0. Okay? Why is that? Well, let's look at, so this is B star. How many rows does it have? 2 to the n minus 1 minus 1. This vector x has size which is 2 to the n minus 1. You have one more variable than the number of constraints. Yeah? So in fact, you can find a non-zero x that satisfies this. Okay? Good. All right. So we're going to fix this x. And now let's look at y, which is bn times x. Okay? So this is a particular a special vector that I'm focusing on, which is in the span of the eigenvectors. Okay? And it's designed so that in this vector y, remember B star is a subset of the rows, right? So B star of x is equal to 0. So if you look at Bn times x, it's going to be 0 outside of H. Yeah? So it has a value for every vertex. And my claim is that outside of H, it's going to have 0 values, just by construction. Yeah? So far, so good? Okay, actually, we're almost done. So, okay. All right, what can we say about an times y? Well, an times y is an times bn times x, which is root n times bn times x, which is just root n times y. Well, we knew that already, right? Because we just have something in the span of the eigenvectors corresponding to eigenvalue root n, so of course this is true, okay? Okay, now here's what we're going to do. In this vector y, let's look at that index that achieves the maximum value and break ties arbitrarily if there are multiple. Okay, so let's choose alpha such that y alpha is max of y0 up to y to the n minus 1. Okay? All right, so we chose a special vector y, and now I'm saying let's look at that index that has a maximum value. Okay? All right, so what do we know about? We know this. An times y is root n times y. In this equality that we just said, root n times y equals an times y, I'm going to look at the alpha coordinate. Okay, let's focus on, this is an equality between two vectors. Let's just look at the alpha coordinate. Okay, let's look at the absolute values. Okay. All right. Now let's look at what's going on. When we multiply, what I mean is you take this product and take the alpha coordinate. Okay, so all right. So what's going on? How do you get the alpha coordinate? So here is A, here is Y. I'm going to take the alpha row of A and multiply it by Y. Right? That's what I'm doing. Right? So when you take this product and multiply by Y, what's going to happen? Well, this has a whole bunch of zeros. The only non-zeros it has are corresponding to edges incident on the vertex alpha. Yeah? Okay? So you can only get non-zero contributions corresponding to every edge, okay, in here. And the further property is that y, remember, is 0 outside of H. Okay? So here's y. It has a bunch of values, but outside of the induced subgraph of interest, it's 0. This matrix has zeros and plus 1, minus 1s, but it's 0 whenever you don't have an edge in the hypercube. So when you look at the product, the only non-zero contributions that you get are corresponding to edges inside of H, incident on alpha. Yeah? Exactly. So the maximum value that you can get here is absolute value of y alpha, which happens to be the largest of the absolute values, right? Times the degree of alpha in H. Okay? Less than equal to. Yeah, this is the largest possible contribution you can get here. Okay? And you're done. This proves that the degree of this vertex is at least root n. Okay? It's a very slick proof. It's really simple. Okay. We're done. We proved that theorem now. Right? Any questions about the theorem itself? So this proves that this vertex alpha, I'm overloading alpha. Alpha now is a vertex, has at least root n neighbors in H. Okay? So we had a very simple sounding statement we wanted to prove. That we look at this induced subgraph, it has at least root n, degree at least root n. And now we proved it by a very simple proof, which basically takes the adjacency matrix, introduces appropriate signs in some very clever way, and then argues about the eigenvalues. Okay. The only fact we used was that by an appropriate signing of the adjacency matrix, we were able to produce a matrix where there were half of the eigenvalues were root n. Okay, that's the fact that we used in this proof. Okay, so fine. So we proved some simple statement, but why is this interesting?
So let me ask you a very important question. So I have an adjacency matrix of that.
Yeah.
Some matrix actually. For that matrix in terms of
The adjacency matrix of the hypercube?
Yes.
It's just the absolute, replace all the entries of A by the absolute values. That's the adjacency matrix of the hypercube. Right? Well, what's the adjacency matrix of any graph? You just have the rows and the columns are indexed by the vertices. Right? You have to have some numbering of the rows, vertices. And the uvth entry is going to be 0 if there's no edge. It's going to be 1 if there's an edge. And what was the property of this matrix? This matrix had the property that you have 0 when there isn't an edge, and it's plus 1 or minus 1 when there is an edge. So this is just a special signing of the adjacency matrix.
You could make the slides naturally if you have additive edges, if you wanted to. I mean, plus 1 for one arrow and minus 1 for the other. I don't know if it helps, but just...
Yeah, okay, that's good. I don't know if an interesting interpretation in terms of thinking of this as a directed graph, but it could be. It could be that there is some interesting interpretation in that way. Yeah, you're right. You can think of this as a directed graph with the signed adjacency matrix. Yeah.
Where did you use the property that alpha had this was maximum across one mod y direction?
Okay, so we're saying, okay, we're going to take this matrix times this vector, and finally we're interested in the alpha coordinate. So how are we getting the alpha coordinate? We're getting the alpha coordinate by looking at this row times this column. Yeah? Okay. So now, what we're saying is, first of all, where are the non-zero contributions? First of all, in order to be non-zero, right? So I'm going to look at the alpha bth entry here and multiply it by y beta, right? I'm going to sum up quantities of this form, okay? In order for this to be non-zero, this has to be an edge. In order for this to be non-zero, this has to be in H. So basically, the only non-zero contributions correspond to edges inside H, okay? And then, what is the value of this contribution? The value of this contribution is either +1 or -1 times y beta. But the maximum, the absolute value of y beta is at most y alpha, right? Okay? So, and that's why. Okay? All right, any questions? Okay, so now let me tell you a little bit about the significance of the result. Okay? Actually, I realize I'm out of time. Okay. Okay, all right. Hopefully I won't go way. So I have to say, I first prepared this for a 20-minute talk at a workshop and actually managed to finish it in 25 minutes. But I was going much slower today. So, okay, so this proof was given by Hao Huang. And he posted it to the archive July 1st of this year. It was submitted to the Annals of Math. And let's see, received when? July 20th, and it was accepted August 28th. Okay, so obviously this is a big result. Doesn't seem like a very big result right now. The reason why it's very interesting is because it solves a long-standing open problem in theoretical computer science called the sensitivity conjecture. Okay, and of course I betrayed this already by the abstract of the talk. I should say that the version of the proof that I just described here follows Hao Huang's construction in his proof. There's some details that were simplified. Actually, this version of the proof was given by Don Knuth. And he actually fleshed out a suggestion by Shalev Ben David on Scott Aronson's blog. Okay, so the original proof by Hao Huang uses an interlacing of eigenvalues argument at some point, and Don implemented a suggestion by someone else that showed that, well, you actually can give a completely elementary, if you don't want to rely on this interlacing argument, you can actually explicitly construct the eigenvectors and so on and so forth. So anyway, so that's the proof that I described, okay? So if you actually go and read Hao Huang's paper, it'll look a little bit different. All right, so why is this interesting? This sensitivity conjecture is all about the relationship of measures of complexity of Boolean functions. So, what is a Boolean function? Boolean function is just a function that maps hypercube to 0, 1. Okay, so it just takes the hypercube and assigns 0, 1 to every vertex, right? So we'll be interested in the following. So if you have a subset of the bits, okay, let's look at x superscript s, which is just the string obtained by flipping the indices in S. Okay, so everybody in S you flip, the rest you keep the same. Okay? Okay. So given such a function, I'll define the local sensitivity to be the following. Okay, S of f of x. It's the number of indices I such that xi, f of xi is not equal to f of x. Okay, so look at x, look at f of x, and consider flipping each of the n bits and figure out for how many of these flips does the value of f change. Okay, that's the sensitivity of the function.
S of fx is the number.
This is the local sensitivity of the function at the point x. Okay, so it's defined.
X was x
Oh, what is x? X is some point in the hypercube. So x is a string of length n, zeros and ones. Okay, I'm looking at the value of the function at x, and I'm saying, if I flipped x, so I look at f x with the ith bit flipped, when is it the case that my function value changes? Okay, this is a measure of sort of smoothness of the function. It's a discrete analog of smoothness. Okay, a perfectly smooth function would not change very much, so it won't be that many bit flips under which it will change. The parity function is very, very sensitive. Any bit flip will change the function. Okay, so this is the sensitivity of the function at x, and the sensitivity of the function overall S of f is the max over all x of the sensitivity. Okay? All right. To say that the sensitivity is low means that no matter where you are, there are not that many bit flips that will cause the function to change. Okay, so that's sensitivity. There's an analogous notion called block sensitivity. So again, you have a local version and a global version. Okay. And with block sensitivity, you have a bunch of disjoint sets of coordinates b1 to bk. And you ask such that for each of these,
So B1 to BK are, when you say disjoint coordinates, so that means
okay,
they have all bits disjoint.
yeah, so b1 to bk are pairwise disjoint. They're all subsets of n which are pairwise disjoint. So they don't necessarily cover everything, but each index can appear in at most one of these BIs. Okay, some indices may not appear in any BI. All right, so let's consider taking the n coordinates and just partitioning them into blocks. Maybe some coordinates you don't use. And the property is that for each BI, f of x is not equal to f of x BI. Okay, so what does this mean? This means that if I flip all the coordinates in BI, the function value changes. All right? Okay, so I can define the local block sensitivity of the function at x, and then I can define the global block sensitivity of the function to be the max over all x of the local version. Okay? All right? Okay. So one simple fact. let me just make sure we are on the same page. The block sensitivity is at least the sensitivity. Does everyone see this? I said that to compute block sensitivity, you need to take the bits, the set of n bits, divide them into subsets of disjoint indices, okay, which have this property. In particular, you can just look at the singleton sets, and this will prove that the block sensitivity is at least the sensitivity, okay? The sensitivity conjecture is all about, okay, so I'm going to go back there, and hopefully I'll finish in just a few minutes. Okay.
The block sensitivity of flipping whole block.
Of the whole block, yeah. Okay. So the sensitivity conjecture basically said that the block sensitivity of F is less than equal to the sensitivity of F raised to some power. Okay, so the the sensitivity conjecture was all about what's the gap between these two measures, the block sensitivity and the sensitivity. Okay, this one says that the block sensitivity is at least the sensitivity, and the question is how much larger can it be? Right, so this we know that this is easy. This is from definition. Okay, and this was the conjecture.
But there's some C, I mean, the conjecture for C.
There exists, the conjecture is that there exists some constant C such that the block sensitivity is at most sensitivity raised to some constant. Okay?
It doesn't say what C is.
Doesn't say what C is. So Nisan and Szegedy conjectured this. Okay. I should say one more thing for context. There are many ways in which you could measure the complexity of a Boolean function. Okay, these are two ways, like how sensitive is the function to flips, to changes, right? But there are other ways in which you can measure the complexity of a function. There's something called the decision tree complexity, right? Can you compute the function by saying, is this bit 0 or 1? Then I'm going to look at this bit, then I'm going to look at this bit, and then so you follow down a tree, right? You just make these decisions, and eventually you say, aha, now I know the value of the function. So imagine a way in which you could describe the function by a decision tree like this, and look at the depth of this decision tree. That's another measure of the complexity of a function. Over all possible decision trees, find a decision tree that has small depth. Okay? So people have come up with different notions of how complex a Boolean function is. And it was known for all of these. This is the other thing. You can also represent the function by a polynomial and ask what's the degree of the polynomial. You can represent the function approximately by a polynomial and ask what's the degree of this approximating polynomial. All of these measures were known to be polynomially related to each other, except for sensitivity. Okay, so everything else, it was known that they're sandwiched between polynomial functions of each other. Okay, and sensitivity was the lone exception. It was the one function that we didn't know somehow belonged to this equivalence class, right? And the sensitivity conjecture was all about saying
C is some number, so I mean, that's why it's polynomial, it's not e to the s of it.
Yeah. So
there's some bound on C and some lower bound.
yeah. So okay, so just to tax you a little bit further, I'll just tell you very quickly what was known. So what was known was okay. So this is known, right? Block sensitivity is at least as large as sensitivity, right? I believe the previous best result was Kenyon and Kutin from 2004, and they showed that block sensitivity is order of e to the s of f square root of s of f. Okay. And another result, this is due to Rubinstein. 95 said that he gave an explicit function for which log sensitivity is okay. Right, so this says that C has to be at least 2. Okay. All right. Now, to complete the whole picture, Gottsman and Lineal in 92, shortly after Nisan and Szegedy came up with this proof, they said that, look, there are a number of measures of complexity, right? There is block sensitivity, there's degree, which I didn't define, but I sort of just verbally said what it was. And Gottsman and Lineal said that if you can address this hypercube question, then you will have a connection between block sensitivity and the degree. Okay? So, without actually trying to define various things, basically they said, and this is not completely accurate, but what they said was that if you can guarantee that delta H is at least some function of n, okay, whatever function you can prove, this will imply that the sensitivity is at least h of the degree of f. Okay, so I want to relate block sensitivity and sensitivity. This relates the sensitivity to the degree. Okay?
So the degree of f is just f.
So what is the degree of f? Represent the function f by a multilinear polynomial, okay, and look at the degree of this multilinear polynomial. So for example, if the function was just the value of the first bit, then the degree of this function is 1, right? It's just x1, okay? If this function was the OR of 2 bits, then you would represent it as x1 plus x2 minus x1, x2. This would have degree 2, right? So there's a unique multilinear representation of the function. The degree of the function is the degree of this multilinear representation, right? So this says that if you can solve this combinatorial problem and prove some lower bound, this means that the sensitivity is at least the same function h of the degree, and what was known already was that the degree of f is greater than or equal to square root of the block sensitivity. Okay, so this was known. This was missing. What we now know from Hao's theorem is that the sensitivity of f is at least square root of the degree, right? And hence this is the block sensitivity f raised to the power of 1/4. C is at least 4. Yeah. Okay. This is actually the best known separation that we know of. So the best known separation we know of is a quadratic factor. So we know that C is at least 2. We didn't know any constant upper bound on C, and now we know that C is at most 4. Right? Okay, so I did advertise in my talk, I'll talk about some connections to physics, but in fact the audience knows way more about this than I do. So I will say that, yeah.
C is less than 4.
Yeah, C is less than 4, right? Good. It's always good to make a few mistakes because it keeps the audience alert. Right? So I'll say one thing. For the physicists in the audience, I wanted to, I'm going to just point you to this paper because this is a paper that says it's written for a physics audience. It's a paper by And you can just look it up by the title. It's actually written for a physics audience. It explains the proof of the sensitivity conjecture in the language of physicists, and also explains that, in fact, this signed adjacency matrix that Huang uses in his proof is really related to the Jordan-Wigner transform that Rajesh pointed out. Okay, so this is stuff that I don't know much about, but you guys should be able to read it very easily if you're a physicist. There's also connections to Clifford algebras. In fact, this paper also points out a bunch of other interpretations of Huang's proof in terms of other objects that we have been studied in other contexts. I think none of this takes away from the ingenuity of the proof. I think the ingenuity was sort of in realizing that, look, this whole thing can be reduced to constructing a certain special signed version of the adjacency matrix, which has some nice properties of the eigenvalues. So in fact, there's a discussion about this on various blogs, and one of them, I think Hao Huang himself responded and said, the history of this was he heard about this problem when he was, I guess he was a postdoc at IIS at the time, and he was really fascinated by it. So went back and to think about it repeatedly. He's a discrete mathematician. He was a student of Benny Sudakov at UCLA, and then he was at a postdoc at IIS, and then he's at Emory now. So he sort of, he heard this problem, I think, from Mike Sachs, and he kind of, it really resonated with him, and he went back. Every time he learned a new technique, he would go and try to think about, attacking this problem. So he worked on it for several years, and then eventually he was writing a grant proposal where, he had want to suggest some method, and actually realized, hey, actually this works. So everything came together, and it's a really short and elegant proof. And there've been many, many attacks on this. This has been a problem that's fascinated people for a long time. And so it's really cool that the eventual resolution of this was by this very nice, simple construction. And further, this construction actually has parallels in math and physics. I guess it just tells us that we should talk more to each other. And hopefully there's something that comes out of it. Maybe there are, I think this particular paper points out that there are certain measures of complexity, I think, in quantum chaos, and again, I don't know anything about this stuff. And just maybe there are some connections with that to Boolean function complexity. So anyway, I encourage you guys to look up these things if you're interested. But thank you. I think I'll stop here. I don't want to take too much time away from lunch.